I'm Tim Ventura, and we're joined today by Holger Thorsten Schubart, the CEO of the Neutrino Energy Group. Holger is a mathematician and entrepreneur with experience in scientific, industrial, and medical technology and business management. He joins us today to discuss his proposed concept for neutrino energy, a new type of energy generation technology that his team hopes will harness the invisible radiation spectrum from space into decentralized electrical power. So Holger, welcome. It is an honor to have you join me today. I first read about your work with Neutrino Energy a few years back, and we'd actually planned an interview for, I think, something like 2019. The pandemic got in the way. So I'm glad that I'm finally able to interview you on this. Let me start out by asking you for an overview of what neutrinos are and how you hope to convert them into electrical energy.
First of all, I also like to say thank you that I have today the possibility to talk to you. And the second thing is maybe it's not only a question of the neutrinos. The neutrinos, maybe this is also maybe the largest error that neutrino energy is not only a question of neutrinos. So neutrino energy gives a name for the neutrino energy. We are using the whole spectrum of different radiations. And the neutrino help us a lot. So the idea was finally, I will go a little bit further. One of the questions is why we have the name neutrino. I can tell you it's simple. When we have some experiments in 2010 in deep mountains in Switzerland, we have some effects, and the professor said so deep, 200 meters under Earth, here is nothing else is arriving, only the neutrinos. And this was for me the birth hour of the Neutrino group. Finally, the effect, what we are talking about, this is a material science effect, and I hope we can answer some question today.
Oh yeah, absolutely. Well, and I should apologize in advance if my questions are too focused on neutrinos. So I went through the website, and I also went through my old notes from a few years back. I know that your vision continuously is being refined and changed over time. So I hope that they're not too far off there. So again, you'd mentioned using the entire electromagnetic spectrum. That's definitely something I want to come back to. Now, on your website, you mentioned that the 2015 Nobel Prize winners, Takaki Kajita and Arthur MacDonald, they had proven that neutrinos are more than simply ghost particles. Can you tell me what you meant when you said that, and why is that important to this?
Yeah, this helped really a lot. You know, that what we are doing is harvesting the energy of vicinity, and mostly the people say, I can't see anything, there is nothing. And so the Nobel Prize helps a lot, because if something has mass, Einstein's formula EmC squared, it's already working. So we have a mass, and we know exactly how much mass we have. We have one neutrino, one electron volt. This is a very small amount of energy, but we know we have 60 billion neutrinos square centimeter every second. So if you have 60 billion, one electron volt, 1 square centimeter, 1 second, it's a weak energy, but in the mathematical addition, it's a huge amount. So we have today, we have the proof. We have, and this was very, very much important, we have the proof, we have energy around us. We have the energy around us. This was one of the main questions, was what has to be answered with yes. And the second question is, do we have any tool which gives us the ability to convert this kind of energy into electrical current? And so today we can answer both questions with yes. We have the energy around us, and doubtless. And the second part, the most important part, is we have today a technical ability to convert this kind of energy into electrical current. And
oh yeah, so if I understand that correctly, and I just want to reinforce that to the audience, is You're not talking about capturing neutrinos the same way that you would capture photons in a solar cell. And the difference would be that neutrino interactions are very, 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 very rare. So what you're relying on, though, is this bulk effect, because there are so many of them coming out of the sun. And you're saying that there is a very weak effect, and it's tiny, but we can harness that, and we can make up for it with the fact that there are so many of them coming out, and they're not absorbed by the atmosphere, obviously. So
You're totally right. So we are doesn't catch neutrinos by catching neutrinos. This is something what the basic researchers do, and this is a really difficult thing. You know, maybe you can catch sometimes a few, and this is a complicated thing. It's not necessary. We just take a part of the kinetic energy, and a part of the kinetic energy will be converted into micro vibration of a special material. This is our graphene. So we have a graphene starts shaking, not in catching neutrinos, but the neutrinos is passing, and passing the neutrinos let the graphene shaking. And if something is moving, energy must be involved, because if there's no move, there's no energy. And look the windmills. This is another dimension, but you can see it with your eyes. So the windmill is turning. The windmill doesn't catch the wind, you know, but the windmill is turning. And this is what we have, is like a very tiny windmill, and the effect coming by the neutrino flux and other invisible radiation. And this is very much important. And I wanted to say, we doesn't catch neutrinos. We're using a part of the kinetic energy.
Okay. And you know what's interesting about that, actually, I have also been following Dr. Paul Thibodeau, and he has what's called the Graphene Energy Harvester. He is doing exactly the same thing. Now, in his case, I believe that they're attributing the energy to Brownian motion and not neutrinos, right? But I think that's, in a sense, that's almost neither here nor there. I think what you're talking about is the same thing. You're taking lattice vibrations in graphene, and you're converting those into energy.
No, Tim, this is, look, Brown motion is just how it works. But the question is, where's the energy coming from? What is the source of the energy? What is the source? Because if something is moving, you need energy, and energy must come from somewhere. So the energy is not coming from the graphene. The graphene is just a quantum mechanical tool, and the Brown motion is just an effect. But the question is, where is the energy coming from? And the energy is coming from the invisible spectrum of radiation, including the neutrinos. So what he does, Professor Thibodeau, exactly, he used the graphene as a tool to convert something, the movement of the graphene, into electron flux on this metal film, and this is DC. And this is finally it's a question, what is the name for it? For example, water. Also, I can remember what our professor said. The power of the water doesn't have any power. Sorry. So when the water it's turning through a turbine, it's cavitation, and also the wind. The wind is finally the same way of energy, and the neutrino is another source. It's the primary source of energy, and this has an effect. And this is just the question of the wording. So when you understand neutrino energy is the total spectrum of ambient radiation, also the artificial radiation, what is also used in this kind of micro vibration, you come close to the idea of the technology what we have. And the same is when you say, oh, it's very weak. Some people say to me, oh, it's too weak. Yes, it's weak, but when it comes to neutrino energy, it comes also to a change of system. Today we have a system that's established 150 years ago. We have large numbers of energy is produced. The AC is produced, it's transported, it's transformed, and finally down transformed and used in little technical gadget. When you use directly the energy of the ambient around, so harvesting the energy of vicinity, and this energy is enough, and you doesn't need to charge anymore this kind of a little gadget. Maybe it's just 2 watt or 3 watt, but if you have millions or 100 millions of these little machines, finally the whole amount of energy, it's the same like if you have 10 or 20 nuclear power stations. It's a totally different way of using electricity.
Yeah, that makes sense. It's massively multi-parallel. And I think that's something that we're seeing in computing, right? Is as computers hit, this is off the wall comparison, but as computers hit Moore's law and a specific chip can only process so much, one of the things that we're seeing is cores are multiplying. And you're talking about the same thing with energy. It's, okay, we may be able to only generate a small amount of energy with each individual graphene unit, but if we run these in parallel and create a massively multi-parallel network, then we can produce large amounts of power. Now, I did want to ask, how did you arrive at the idea that ultra-thin layers of graphene would respond to the passing neutrinos and the EM energy? What brought you to the graphene as a tool?
All the research came from the solar cells. So we and some professors were around 15 years ago tried to make particles smaller. And when you make particles smaller, you make surface larger to increase the output of solar cells. And they found out when they come to the little particles of the graphene, they were starting an atomic vibration at nanomaterials. So this atomic vibration at nanomaterials is the idea of the beginning of the neutrinovoltaics, because this kind of vibration, the question was, this is exactly what we did and in this deep mountain in Switzerland. And the professor said, wow, can you see this kind of vibration? How it's possible? And some students asking, and he said, here in this, only the neutrinos can have this effect. And the problem is, we all only knowing this, what the official knowledge is so far. And there are, I think there's a lot of phenomena which are still undiscovered. There's a lot of things to find out. But when we found out that we have this kind of atomic vibration at this level, and we see the effects, then the idea came: if something is moving, there must be energy inside. When something is moving, it must be a possibility to convert this kind of moving without a transformator, because the production of current, as we do it so far, is always the same. We use a transformator and a magnet, and we need the conversation of something else into this turn of the magnet and the transformator. And this is finally a little bit like the same in another size. So what happened is something is moving, and this moving is converted into electron flux on a metal layer. And the way of the branch moving is to make it, you need that the electrons run in one direction. And this is a little bit the pattern what we have. So when you turn a little bit this kind of layer, so this is what we describe in a pattern. If you normally the electrons go in all directions, and a little bit the trick is to make it so let the electrons run in one direction. Because when the electrons start in one direction, you have the DC. If electrons run in one direction, starts the DC. And in this kind of DC, it's very weak, but it's a little bit the same like in a solar cells. When you remember the first solar cells came in the calculators, there were just a little solar cells inside, and when we were at school, we are putting our sum on it, and all the numbers disappeared, and the light came, and it's already, and this is finally a little bit the same. That this kind of small neutrinovoltaic cell, if you have, and this is the big advantage of physical phenomena, you can double it, you can scale it. It's in chemical processes, it's not possible, but mostly not possible. But in physical processes, yes. So if you have a double size, we have double power output, and this makes it so interesting. So that we say, oh, we have just a little bit of energy, but if we have double size, we have double this little size of energy. And when it comes to any kind of electrical gadget, it's always a question about how much energy it's needed, and how much energy, it can be harvested. And it must become in a balance. And you maybe we also will buffer a little bit. We have an interface inside. But finally, the idea is that really any kind of electrical device can be using the energy of vicinity because it's enough there. And this in energy, it's just 2 watt, 3 watt, 5 watt, whatever. But finally, it comes to the situation that we doesn't need this kind of electrical system as we have. We have it, maybe we will have it the next 20 years. But I'm believing surely that maybe in 10, 20, 30 years, all this kind of electrical gadget doesn't need anymore any kind of charger, any kind of batteries, because we know today we have the energy around us. So it was just a necessary step, necessary engineer work to create this kind of converters. And this is what we are doing. We are creating converters because we are now knowing we have the energy and we have kind of tools to convert it. And this professor, what you talk about, I really appreciated work because he shows a little bit how it works, why it works. And I'm sure, as I can see in our laboratories, there are many, many ways to increase it. Finally, there's no perpetuum mobile at all. So it can never comes more energy out than energy comes in. But at this point, the Nobel Prize was so important because it was the first question. Because the Nobel Prize gives finally the approval that we have this kind of energy around us. Because before people say, oh, we see nothing, there is nothing. How you want to take energy from nothing because no perpetuum mobile is existing. And so I was really happy at this day the Nobel Prize was given. And it also shows us that we have used the right name, because the way the name Neutrino Energy is, this was a little bit rude to use this name. And the people say, oh, you can't catch the neutrinos. But I was sure that it was the right way. And after the Nobel Prize was given, we are totally sure. And also the question is, for example, when you drink a coffee, the question is how much coffee is in the coffee. If you have a chemical professor, he will tell you, no, there's H2O, there's a lot of other things inside. So the question is, how much neutrinos in neutrino energy? I can tell you for sure, we have a lot of neutrino energy in neutrino energy, but we also have other effects.
Well, yeah, and that's very important because in today's airspace, or in today's world, if you will, it is crowded with electromagnetic energy, right? And a lot of that is outputs. I mean, not only do you have solar radiation coming in, but you also have electromagnetic energy all over the RF spectrum, and that just continues to increase, right? And they're calling it electromagnetic pollution now. And so all of these energies, even though they're all weak, they contribute to these graphene lattice vibrations, right?
Absolutely, you're totally right. And it's also a question, for the consumer, finally, it works. And the question is not how much percent is the neutrino flux, how much is the, this is the question. It works also if you use your smartphone, the people use it and not ask why it works. And we are, we had a lot of controversial discussions, and we even have a lot of problems when we started to do this, because the people said it's impossible. It's an impossible physical model. And today, I'm so happy about that. All this approval is there, that we have in the spectrum of the invisible radiation, including the neutrinos, we have so much power around us. I just give you 2 numbers, just to understand. And it's one single day. The radiation, just neutrino radiation, and I'm not talking about the others. The neutrino radiation was arriving on Earth. It's 5,000 years energy consumption, one single day. And one single day, the radiation, what is coming, represents more energy than all fossil fuels combined, in one single day. And what we are doing, look, Tim, we are fighting wars. We have a lot of problems. We are polluting the earth. We have, we are still grabbing in the ground like 150 years ago. We are flying to the moon. We are working with computers. But if it's come to energy, We're still using the old system. And this is the question, why? You know, do we have not smart scientists? I think we have a lot of smart scientists around us. The question was, the smart scientists were not allowed to start to eat a little part of this established system. And today I'm very happy because now it comes to a change. People understand we need solutions for the future. And I think it's really the best time now with this concept to come in the market. So we have the approval that it works. We made all the financing by ourselves. Nobody was helping us. The people were really attacking us at the beginning. And I'm really much convinced today that maybe even at the end of the next year, we have Power Cube ready to touch. And also this pi car, I hope that I have a few words about a pi car. This is the next.
Oh yeah, yeah. Well, and I would love to come back to let me come back to the pi car in just a moment, though. So what I wanted to ask was some of the experimental stuff. So you guys are using multi-layer graphene systems, right?
Yeah.
And that's, again, that's one of the ways of making this thing massively multi-parallel is not only would you have separate units, but you have multiple layers of graphene to try and capture as much energy in that spatial area as you can. So in terms of experimental stuff, how much energy have your prototypes been able to generate so far?
Look, I want to tell you one very important thing. When it comes to the photovoltaics, you only can work in the second dimension because the photovoltaic cell needs the light. So if the cell is behind the other, it doesn't work at all because no light is coming. And the neutrino cell, so one layer of neutrino cell is much weaker. It's very weak. But we can work in a third dimension. This is a big advantage because the neutrinos penetrate everything. So the kinetic energy is not only given in the upper layer, so it's going through. So we can work in a third dimension. So we can say we have on 1 square meter, and sorry not to have the square feet, we endure have the square meter. In 1 square meter, we have, you know, this is the question of how much energy is coming in. When we have it 22 degrees, if we have a normal circumstances, not a lot of external artificial radiation, we have at the moment we have, this is approved by the court because we did it to show the 3.6 watts square meter. So if it means 3.6 square meter, 0.1 millimeter size of this metal, you can calculate that if you have 1 cube of 1 cubic meter, that is a theoretical amount, it's 36,000 watt a square meter. But nobody will have a cube like this size. So the square centimeter is 3.6 watt. Under circumstances that it's 22.6 degrees, humidity of 30%, and no artificial radiation. And this is, we talk about, we are not having energy production, we have an energy conversion. So finally, it's a question, and this is exactly what you said at the beginning, when you come in a field of electromagnetic fields, or also the heat's coming on it, the vibration is stronger. As more vibration you have, as more energy output you have. So finally, it works under different circumstances, and it has a minimum. It even worked 20 degrees minus. We have tested it in Sweden in a very cold winter, so, but it has less output. And if it's in countries where it's warmer and you have all this kind of more movement, more shaking of graphene in warmer areas, you have more output. And this is fine. This is because it's a converter. It's always you only can have that what is coming in, or less of this because you have a lot of losses. But finally, this may let us convince a lot also to improve it, because as we talked at the beginning about the neutrinos, we know how much energy we have per second a square centimeter. So when we see we only have this 3.6 watt, this is just a little part. It's not a lot. So I know, same like the solar cells has improved within the last decades. I'm totally convinced that we are also able to increase the energy output of the cells within the next years. But even what we have today, this is just the first generation of neutrinovoltaic cells when it's come in the market. It's strong enough. It's strong enough to power all that what has to be powered. And sometimes the people ask me, why, Holger, you not produce this? I can tell you very simple. look, Tim, there are hundred thousands of different applications for this kind of technology. And it's not just you bring a product in the market. This technology is really a quantum jump. It's a big change, a big transformation in the, if it comes to, it's a next step at the electrical age. Using in large scales the energy of the ambient energy, the energy of vicinity by using this kind of graphene tools. And I think in a couple of years it will be common. This is technology. What is always, if a new technology is coming in the market, people are scratching their heads and having a lot of opinions, and but it's finally there's no way out. This is and all kind of production, whatever, any kind of other electricity. I will tell you very simple. I all like this, but production of energy is something completely different. Production of energy is something complicated, technical, complicated. That's what we have. It's just a simple way of converting.
Yeah, and so you were saying 1 square centimeter, then it's about 3.6 watts. Now, experimentally, were you able to demonstrate that experimentally? And I think you also mentioned in different temperatures, in different areas, yes, the output was different. But was that experimental, or is that kind of a theoretical model based on size?
Both, we have both. We have both. We have both. We have this kind of experiment. We're still doing the experiment. We have some universities doing the experiments, and this is finally a question of the calculation of how the tool works, how quick the tool works. And we have a multi-layer. If you have one layer, it's a little bit of output, but as we are talking, the penetration it's there. So you can make a multi-layer. If you have a multi-layer, you have more movements, because it's not like a solar cell which only can use one layer. So we have a multi-layer, so this gives the highest effect. So we tried up to 12 layers, and and what I want now, I will hire around 1,000 engineers, the best engineers at all. And we want to set them in some new labs. We are already found the places. We already found some university. And we will make this finance. We make this private finance for this. We use this engineers and say, look, we have already this kind of movements. We have the output of 3.6. And now your duty is just to find a way to make it better and better and better. And this is normally what I expect, that maybe governments or whatever is working on it. But it's not like this. There were just a few, at the beginning, just a few scientists found this kind of, they had this kind of findings. We're thinking about what is possible, and they're working in the labs. And so I'm very happy today also to have the opportunity to talk about, because this is necessary that people understand this phenomenon. They can simple double check it. They're also in the US, there's a couple of research institutes which already shows the movement of the graphene. They're not talking about neutrino energy. You have the other astrophysics, they're talking about the neutrinos and catching. But finally, it's a combination of the astrophysical point and the material science point. And this together gives the idea of neutrino energy.
Yeah, no, and it's a compelling idea. It's been, for me, this has been, again, that's why it's such a privilege to be able to interview on this. I've been excited about this for years now. So I do want to touch on the car pi, or the pi car, depending, so can you tell me how the concept for this kind of came about? I mean, I know that electric vehicles are super popular now. So it's not a stretch to say, okay, we have this energy conversion device, we'd like to use it for a car. What was it that made that a direction for you?
Look, for me, it's like the car. Yeah, I come of the generation where the V8 are, I love it. All this kind of big US machines. And now, totally, as you say, now this kind of electrical vehicles coming. And why the electrical cars are coming? The electrical cars coming, why? Because the audience is thinking electrical cars are clean cars, green cars, super green cars. But Tim, that's not true. When the car doesn't have a pollution directly, but finally it's a question where the energy is coming from. And when the energy is produced in a power plant where it's burning fuels, finally there is balance of this car is not there. The car is even worse than a normal engine. And it was the, and it's, I can talk about Germany because we have a lot of car manufacturers, the best of the world. And they come to the people and say, oh, now you have a clean car, no pollution at all. But it's how you can say it. And how you can sell it. And they charge the cars, and all the owners are proud. And I'm a little bit sorry for the owners because they are really believing in it. They're believing in it that they have a car that is clean, but it's a lie. Like this scandal of this diesel scandal when they change it, and it's a big lie. So what our idea was with the engineers was to find a way to make the car really clean. There are two ways, of course. One is that it's charged by just a real green energy. If it's charged by real green energy, I really appreciate this, absolutely. And the other way is, but there also the energy must produce somewhere on the central system. And there's a lot of weak points because you have not enough charging stations. There's a lot of, it's impossible because it's a question of mathematical calculation of the ability to have enough AC everywhere. And you will find out that if you have maybe 1 million cars at work, if you have 2 million cars, it even becomes a system, becomes weak. But only in Germany, we have 50 million cars. I don't know how many cars you have in the US, but I think even more. And how you want to change all these cars? It's impossible because you doesn't have this kind of energy. It doesn't work. It's a mathematical, it's just a calculation. So we were thinking about to create something on our point of view to say, look, the car is parking on the road. And everybody knows you go out to your car and it's so hot and it's warm. You open the windows, you make the air condition on. And why is the car so hot? The car is not hot because it's even hot if there's no sun. The car is hot and warm because a lot of radiation influence is on a car. And when it's the real as the sun, it's so hot that you can even make your eggs on it. It's what is warm? Warm is energy. And if you start the engine, if you open the windows, if you start air condition, you are destroying energy. You're destroying energy. And our idea was to using this energy. So we know when you just think the car is a plate where you cook. And yet now imagine you need to take the power of the grid to make the car becoming this temperature. You need more energy than a household with 4 people need a whole month to make your car hot, and it becomes hot in 1 hour. So you can imagine how much how much energy is catched in this kind of car. And we were thinking about how can we take it, this energy, what is already in. And our idea was to using our cells to make it in between the empty space of the car. So the car is parking on the road on our system. We have this kind of neutrinovoltaic cells inside in all these empty spaces. And the car, during its parking on the road, it's collecting the energy of vicinity, having the micro vibration, taking the DC, store it in a buffer battery, and you have it. And the other thing is just, Tim, is just a mathematical calculation about how quick you want to run, how long you want to run, how much energy you need. So you park, you drive slowly, and in the past we are talking about quick cars, strong cars, a lot of horsepower, but all this is not needed. It's not needed, especially in the big cities. This urban traffic this is a traffic where you go in the average speed 30 miles, 40 miles, maybe. In all this kind of third world countries where the in China, in India, there's this big center. So the cars are always anyway in a traffic jam. And to move a car under these circumstances, so Tim, you doesn't need a lot of power. It's not a lot. And if you understand that the whole cube of your car can collect so much energy that it's enough to use it into the DC, what is needed to drive. So in one single hour, you know, in one single hour with the 30 degrees outside, a car is collecting enough energy for around 100 kilometers, maybe it's 70 miles. And cars mostly are parking somewhere. They are on the road, they're parking, they are waiting, they are collecting the energy. And the energy it's after this is gone, it's lost. And this was the idea of the car pie. The car pie is just taking this energy and using it under the electrical way, as it's so popular now. But having a car, what it's parking on the road when you come home, doesn't need a charger, just staying and waiting. And then, of course, for acceleration or climbing up hills, maybe you need more energy in this moment than the converter cells give. So you need buffers. So you have supercapacitors, you have buffers. So the car is collecting the energy, have the buffers, and if you need it, you have it. This is a simple idea behind.
Yeah, the self-charging car essentially. So it's going to be taking advantage of this ambient energy, and again, that could be electromagnetic, it could be Brownian, it could be neutrinos, it could be a
Brownian is no energy. So the Brownian is,
Brownian is a result of the energy.
It's just the way how it works. So the energy must coming from somewhere. The energy coming from the radiation around. It's in the conversion. It's the same as I explained at the beginning. And this kind of micro vibration we're used for. And this is the electrons start moving. And this is you know in all this kind of cell. And this is finally at the beginning we talk about the little gadget. Now we talk about the car, but finally you can use this technology everywhere. You can make it in the wall of your home. You can make it in the backside of your television. You can make it when this cell's coming on the market. You can have it in 100,000 different sizes. Yeah.
Again, the concept behind this is wonderful. I love big ideas like this, and this is one of the best. Holger, I want to thank you again for your time today. We're just about out of time, but I want to thank you so much for joining me. And is there a place where people can learn more about you, where they can learn more about this idea?
Of course, Tim, and first of all, thank you very much that I have the possibility to talk some words. You know, this is exactly what I want, that people understand it. This is not a joke. This is not a trick. This is real physics. This is having energy on one side, having a converter, and having electrical current on the other side. And it just I see many people already in the world trying and testing and making it. And it is my dream. This is my dream that we have with this technology. You know, for me, I donate my so this income. What is coming for me? I made my money before in other fields, and I just want to see this project fly. And I have children, and sometimes I will have grandchildren, and I think it's so much necessary to have this project now on a run. It's not only a question of climate; it's only a question of the wars in the world. Because geopolitical conflict, and this is Tim, this is true, are mostly in saving and finding the last resources of fossil fuels. And this is what makes me proud, that we also have a peace project. And if people want to learn something, I just suggest we have a lot of on our homepage, but there are also a lot of scientific publishings already in this field of the graphene behavior, the micro vibration, of course, the neutrinos, and you know, just the audience has to make a combination in the mind to understand that neutrino energy is it's more than catching something. No, it's a concept, totally concept change. Thank you very much, Tim. It was a very big pleasure for me.
Thank you again, sir.
Thank you.